For as long as humanity has looked upward, Polaris has burned with a quiet certainty. The North Star, suspended in the northern sky, unwavering, eternal, has been the compass of countless generations. Ancient sailors steered their wooden vessels by its glow, trusting it as though it were carved into the very architecture of the heavens. For them, Polaris was not just a star, it was a promise of direction, of return, of home. And yet, beneath this constancy lies a contradiction so unsettling that even modern science struggles to grasp it. The star that once guided empires refuses to be pinned down by the tools of our most advanced age. Its light wavers in ways it should not. Its distance shifts, depending on who measures it and how. Instruments launched beyond our planet, satellites with lenses polished to perfection, return numbers that do not agree. Astronomers compare notes, and what should be a simple truth dissolves into discord. There is a paradox here, one that speaks to something deeper than astronomy. Polaris is the anchor of our maps, the still point by which we have charted oceans and skies. But in the language of science, it is the one object that resists certainty, a star that will not yield its exact size, its distance, or even its pulse. If the very light that defines our direction cannot be measured, then what does this reveal about our pursuit of knowledge? What does it say about our ability to capture the universe in numbers, to press infinity into the boundaries of human understanding? Polaris shines on, eternal in myth, elusive in fact, a beacon that refuses to tell us where we truly stand. It begins as a tale of trust. For millennia, Polaris stood almost fixed above the northern horizon, the still point in a turning sky. Navigators learned its language before they learned maps. Poets borrowed its steadiness when they lacked their own. Yet, the closer astronomy came to the North Star, with glass, mathematics, and orbiting instruments, the more that steadiness unraveled into questions. The star that anchored journeys began to slip away from certainty, as though the universe had kept a small private riddle in the very place humanity thought safest to look. The modern chapter of that riddle was written when astronomers recognized what Polaris truly is, a classical Cepheid variable, a star whose rhythm, its period of brightening and dimming, links directly to its true luminosity. Henrietta Leavitt's discovery of this period luminosity law more than a century ago turned Cepheids into mile markers of the cosmos, letting astronomers measure distances across the galaxy and far beyond. Polaris should have been the most cooperative of these beacons, bright, nearby, exemplary. Instead, it is the rebel in the family, ... Even its singleness proved illusory. Through small telescopes, observers since the 18th century could glimpse a faint companion, Polaris B, set off from the main glare by an easy separation on the sky, first noted in the era of William Herschel. But only in the 21st century did the Hubble Space Telescope push its optics to the edge and resolve an even closer partner, Polaris AB, pressed so near the primary that it had long eluded direct sight. The imaging confirmed what dynamics had hinted. The North Star is not one voice, but a small chorus. The bright supergiant Cepheid, Polaris AA, attended by a close dwarf companion and a wider, older one. The guide star of legend is, in truth, a triple system. Multiplicity alone need not disturb a cosmic yardstick. Cepheids in binaries can still obey Leavitt's rule if their pulses are steady and their distances well known. But Polaris would not stay tidy. Over the last century, its heartbeat changed character. Its pulsation amplitude, the swing in brightness across each roughly 4-day cycle, faded dramatically through the 1900s, leading some to wonder if it might be drifting out of Cepheid behavior altogether. Then, unexpectedly, the star's variability stirred again, the amplitude reviving after decades of decline. The seemingly predictable metronome of a standard candle had hiccuped, and with it, confidence. Period, too, would not hold still. Long baseline monitoring showed that the length of Polaris's cycle has been changing over time, an evolution that can carry signatures of interior structure and stellar age, but in Polaris's case, points to complexities not fully captured by simple models. The very star chosen by classrooms to illustrate constancy became the counterexample that professors must now explain. In scientific prose, this reads as secular period change and temporarily varying amplitudes. In human language, it is a steady light that refuses to keep steady time. If its pulse raised doubts, its distance deepened them. Ask one instrument, receive one answer. Ask another, receive a second. Some analyses argue that the North Star sits closer than the traditional figures suggest, near 100 parsecs, about 320 light-years, while other measurements place it roughly a third farther away, around 130 parsecs, about 430 light-years. The discrepancy is not a mere bookkeeping error. For a Cepheid, distance feeds directly into its intrinsic luminosity, and thus into the calibration of all other Cepheids. A mismeasured North Star threatens to tilt the ladder by which other galaxies and the universe's expansion are scaled. Gaia, the European Space Observatory designed to fix stellar positions and parallaxes with exquisite precision, should have settled the matter. Yet Polaris is very bright, and very bright stars have been difficult terrain for Gaia's earliest catalogs. Sensors saturate, calibrations bend at the top end, and subtle zero-point biases creep into the reported parallaxes. For most targets, those corrections are manageable. For a flagship Cepheid, the uncertainties echo. Even as Gaia's data improve, the caution label for the brightest objects remains. The North Star sits exactly where measurement is hardest: dazzling, complex, and scientifically consequential. Companionship complicates the picture further. The close dwarf, Ab, orbits the Cepheid on timescales of decades. Their mutual dance shifts lines in the spectrum and nudges the photocenter on the sky. To disentangle distance from motion, pulsation from orbital tug, astronomers have braided together techniques: high-resolution spectroscopy for radial velocities, space-based astrometry for parallax and proper motion, and ultraviolet imaging to lift the Fate companion out of the glare. Each new observing campaign sharpened some features of the portrait and blurred others. Bind the pieces too tightly, and one forces the data to fit a story. Leave them too loose, and the story dissolves into noise. Polaris seems to prefer the latter. As the measurements multiplied, a pattern emerged, not a solution, but a mood. Polaris does not break physics. It resists simplicity. The period luminosity relation remains a pillar of cosmology, and yet the brightest, nearest classical Cepheid keeps slipping sideways from its template, as if to remind investigators that laws live in populations, not in single stars. The star's interior may be in a transitional evolutionary state, crossing the instability strip in a way that warps its pulse. Energy transport, convective overshoot, rotation, and mass loss can all bias what appears at the surface. In a multi-star system, those private interior stories whisper into the shared light, and telescopes, however perfect, must read a script written by 3 actors with overlapping lines. This is why small numbers matter. A fraction of a milliarcsecond in parallax, a few seconds drift per year in period, a % or 2 of amplitude revival. These become the plot twists. Catalog papers discuss them as 0 points and error budgets. Mission pages caution about bright end performance. But beneath that technical language is a philosophical tremor. Humanity asks the cosmos for a ruler, receives a heartbeat, and then finds the beat changing as the ruler is raised to the light. The North Star glows with a kind of irony, the emblem of direction, the case study in uncertainty, and still it guides. Sailors can find latitude by its height. Children can find north by its gleam. On the canvas of the night, Polaris remains what culture made of it, a fixed idea painted over a moving truth. The scientist's duty is different. The task is not to preserve the myth, but to measure the motion, again and again, with instruments good enough to be humbled by what they see. In that humility, a deeper wonder grows, the sense that even the most familiar star can become newly strange when looked at closely enough. By the end of this beginning, the mystery stands fully introduced. The star is a Cepheid that behaves like an exception. It is a triple system, masquerading as a point. Its distance sits on the fence between two solutions. Its pulse, once fading, has stirred again. The North Star holds steady for travelers and unsteady for theory, as though nature had split a single object into two versions, one for human eyes, another for the patient arithmetic of telescopes. What changed inside Polaris to bend its rules without breaking them? Is the culprit the hidden choreography of its companions, the shifting physics of a star in passage, or the limits of instruments staring too hard at brightness? The puzzle of Polaris did not end with the realization that its light flickers against the laws written for Cepheids. Instead, it grew more intricate as each generation of astronomers returned to measure it anew. Every instrument, every mission, seemed to peel away one layer of the mystery, only to expose another beneath. In the late 20th century, when the European Space Agency launched the Hipparcos satellite, the hope was simple: to end centuries of guesswork. Hipparcos would measure parallaxes, tiny shifts in stars' apparent positions as Earth moved around the Sun, with a precision impossible from the ground. For most stars, it delivered. But when the numbers for Polaris were published, astonishment followed. The parallax implied a distance much shorter than the astrophysical models required. Instead of being nearly 430 light-years away, Polaris appeared closer, nearer 323. The difference was not trivial. It suggested that the Cepheid relation, so carefully built on the assumption of Polaris's steadiness, might be skewed at its brightest end. The irony was unavoidable. The North Star, chosen as a yardstick, might itself be warped. Later, the Hubble Space Telescope joined the chase. With the fine guidance sensors, devices designed for precision pointing, astronomers attempted to refine the distance. The result leaned toward the larger value, supporting the longer yardstick, as though contradicting Hipparcos directly. The community split between camps. Some trusted space astrometry, others favored stellar pulsation models. Both carried weight, neither was decisive. What was meant to resolve ambiguity had, in effect, deepened it. As the 21st century unfolded, Gaia became the next arbiter. Its detectors swept across the sky, building the most ambitious three-dimensional atlas of the Milky Way ever attempted. And yet here, too, Polaris slipped between certainties. Because it is too bright, it saturates the sensors. Because it is part of a multiple system, orbital motion muddies the parallax. Gaia's catalogs list a distance, but every release is accompanied by cautionary notes. Treat bright stars carefully. Trust, but with reservations. Even in the era of precision cosmology, the North Star remains a grain of sand in the lens. If distance defies closure, brightness compounds it. Classical Cepheids follow a law. The longer their pulsation period, the more luminous they must be. Plot the data, and Cepheids fall neatly along a line, Henrietta Leavitt's cosmic ruler. But place Polaris on this chart, and the point will not align cleanly. It shines brighter or dimmer, depending on when and how it is measured. Astronomers tracking its amplitude across the 20th century saw a steady decline. As though the star were calming, its oscillations fading towards stillness. For a time, speculation grew that Polaris might stop pulsating entirely, abandoning its Cepheid identity. Yet in recent decades, the variability revived, the star's pulse beating louder again, defying the trend lines drawn for it. A Cepheid that changes its mind mid-course unsettles more than equations. It unsettles cosmology itself, because these stars are the lighthouses by which distances to galaxies are set. If one lighthouse flickers, how many others may hide small flickers that we cannot yet see? The Hubble constant, the rate of the universe's expansion, depends critically on Cepheid calibrations. And the Hubble constant itself has become a battleground, with local measurements and cosmic microwave background estimates disagreeing by a margin larger than errors should allow. In that tension, Polaris looms silently, as though whispering that the first rung of the distance ladder may still be unsteady. But science is relentless. Polaris has been dissected not only with photometry, but with spectroscopy, splitting its light into rainbows and watching spectral lines wobble with each heartbeat. These wobbles reveal the star's surface rising and falling, the rhythm of a vast gaseous body, inhaling and exhaling. They also betray the gravitational pull of companions. The hidden dwarf, Polaris AB, leaves faint signatures in ultraviolet and shifts in radial velocity curves. It is faint compared to its giant sibling, but in orbital mechanics, even a small companion can complicate the dance. Some theorists suggest that unseen tugging could explain the irregularities in the pulsation period, like a drummer playing against a subtle offbeat. Others look inward, to stellar evolution. Polaris sits at a crossroads, a yellow supergiant, perhaps crossing the instability strip of the Hertzsprung-Russell diagram, not once, but multiple times. Each crossing can alter the pulsation characteristics, bending the expected relationships. Add in mass loss through stellar winds, internal mixing of heavy elements, and rotation, and the equations begin to wobble, just as the light does. Polaris may not be breaking laws. It may simply be living at a point where several laws collide, producing behavior that looks anomalous only because our models are too simple. Yet, for all the attempts at explanation, the emotional paradox remains. Humanity has crowned Polaris the symbol of steadfastness, the eternal guide. But inside observatories, it is the object that slips through certainty's grasp. Sailors trusted it without question, while astronomers drowned in questions. It is both the firmest anchor of the night sky and the most elusive when placed under the microscope of science. The philosophical echo is impossible to ignore. If we cannot fix the coordinates of the very star that defines direction, what hope do we have of fixing our coordinates in the universe? If a single Cepheid at our doorstep resists clarity, what hidden ambiguities lie in the distant galaxies whose light we stretch into cosmology's deepest claims? Perhaps Polaris's refusal is not failure, but a lesson that certainty is a human demand, not a cosmic obligation. What is Polaris truly telling us? Is its rebellion a quirk of companions, an evolutionary hiccup, or a deeper warning about the very yardsticks of cosmology? The unease surrounding Polaris grew heavier when its behavior was weighed against the framework of stellar physics. Cepheid variables were not supposed to behave this way. By the early 20th century, Henrietta Leavitt's discovery of the period luminosity relationship had turned Cepheids into the yardsticks of the universe. Their value lay in their predictability. Measure the time it takes a Cepheid to brighten and dim, and you know its intrinsic luminosity. Compare that to how bright it looks, and you know its distance. It was a law as reliable as the swing of a pendulum, a foundation for the scale of galaxies. But Polaris refused to obey. Astronomers charted its pulsations across decades and noticed something unthinkable. The amplitude of its heartbeat, the amount by which it brightened and dimmed, was fading, almost collapsing to zero. For a Cepheid, this was heresy. Such stars are supposed to pulse with stability, their variability a gift of physics, not a fleeting accident. As the 20th century closed, Polaris seemed ready to surrender its identity as a Cepheid altogether. What would it mean if the North Star stopped pulsating? Could one of astronomy's most important calibration points be slipping silently out of the category upon which entire galaxies' distances were built? The scientific shock rippled outward. If Polaris, the closest classical Cepheid, bright and accessible, could disobey the rule, then perhaps the rule itself was more fragile than believed. The standard candles of cosmology, used to measure the scale of the universe and to anchor the expansion rate known as the Hubble constant, might flicker in ways unseen in more distant examples. A single star's quirk threatened the scaffolding of modern cosmology. The distance problem sharpened the alarm. When Hipparchus published its parallax measurements, placing Polaris hundreds of light-years nearer than astrophysical models required, disbelief followed. The disagreement was not a mere rounding error. It implied that either the models of Cepheids were wrong, or the parallax measurement, once heralded as definitive, had stumbled on one of the brightest, most important stars in the sky. Hubble's later instruments disagreed, pushing the star back outward. Gaia's catalogs hedged their numbers, noting saturation and systematic errors. What should have been the most elementary question, how far away is the North Star, became the most stubborn riddle. This was not just a local embarrassment. Cosmology builds ladders of distance. Parallax calibrates Cepheids. Cepheids calibrate Type 1a supernova. And supernova calibrate the expansion of the universe. If the first rung is crooked, the entire ladder bends. Astronomers realized that Polaris was not a peripheral nuisance. It was central. Its refusal to be measured with precision cast a shadow over the distance scale itself. The star's internal physics raised further unease. Cepheids are understood to pulsate because they sit in a region of the Hertzsprung-Russell diagram known as the instability strip. Hydrogen and helium ionization zones within the star trap and release energy, setting up rhythmic oscillations. The period of these oscillations depends on the star's mass, radius, and evolutionary stage. But Polaris's period was drifting at a rate inconsistent with simple evolutionary models. Its amplitude was reviving after decades of decline. Its pulse seemed to carry a story about its core, but the story contradicted the textbook. Some researchers proposed that Polaris might be in a transitional evolutionary crossing, moving across the instability strip for a second or even third time. Others pointed to mass loss or rotational mixing, processes that could distort the clean predictions of stellar evolution. Yet no single explanation tied together the amplitude collapse, the revival, the drifting period, and the inconsistent distances. It was as if Polaris had chosen to collect every anomaly a Cepheid could host and display them in one star. For the astronomical community, the shock was twofold. First, the practical. If Polaris cannot be trusted as a calibrator, the cosmic distance scale must be re-examined with caution. Second, the philosophical. If the most familiar star in the night sky conceals mysteries this deep, what confidence can we hold in the certainties we ascribe to stars far more distant, observed with far less precision? The paradox pressed itself into the language of research. Papers spoke of the Polaris problem. Conference slides listed it as an open question, the kind that hangs uncomfortably in a field built on precision. In the late-night discussions of observatories, one hears the frustration sharpen into wonder. How can the compass of humanity mislead the yardsticks of science? By now, Polaris had ceased to be merely a star. It was a contradiction wrapped in light. To the casual eye, steady as ever, marking north with patient fire. To the astronomer, unstable, confusing, refusing to fit. The paradox widened, not narrowed, with each new set of data. Instruments built to settle disputes instead made them larger. If the nearest Cepheid can defy its own law, then is the law universal? Or have we mistaken a local riddle for a cosmic truth? The disquiet around Polaris intensified when astronomers tried to reconcile observation with theory. Stellar models predicted a certain mass, radius, and age for a Cepheid of its period. Yet when Polaris's properties were folded into these frameworks, contradictions piled up. Its observed luminosity did not match its measured distance. Its period change seemed too rapid for a single evolutionary crossing, and its companions, faint but present, disturbed the clean simplicity of treating it as an isolated star. The closer one looked, the more Polaris slipped away. High-resolution spectroscopy revealed subtle oscillations beyond the principal pulse, hints of additional modes stirring in the star's envelope. These secondary vibrations did not sit comfortably within the Cepheid template, as though Polaris were improvising variations on a rhythm rather than playing the expected note. Some astrophysicists suggested resonant interactions inside the star, with layers of ionized helium and hydrogen competing to set the tempo. Others wondered if the presence of the nearby companion, Polaris AB, injected gravitational complexity that slightly warped the pulsation. The star was not offbeat so much as polyphonic, humming in layers science had not fully anticipated. The revival of its amplitude, after decades of decline, stunned even seasoned observers. Cepheids were expected to evolve smoothly, their variability dampening or amplifying in predictable ways as they crossed the instability strip. But Polaris seemed to break the sequence, recovering strength like a fading signal suddenly amplified. It was as if the star refused to fade quietly, insisting on being heard again. Astronomers struggled to decide whether this was a temporary reprieve, a new stable phase, or a prelude to further instability. The companions added another layer of shock. Polaris AB, the hidden dwarf, orbits close enough to tug subtly on its giant sibling. Detecting it directly with Hubble confirmed suspicions long harbored in spectroscopic data. Yet, modeling the system produced new uncertainties. Orbital mechanics altered the light curve, spectroscopic velocities carried mixed signatures, and disentangling pulsation from orbital motion demanded assumptions that could not be proven. Even the wider companion, Polaris B, introduced its own complications, raising the possibility that the system's origin story, perhaps a complex dance of capture and formation, might hold clues to why the primary star behaves so strangely. Astronomers began to whisper a troubling thought. Perhaps Polaris is not merely a peculiar Cepheid. Perhaps it is the harbinger of hidden complexities that affect Cepheids more broadly. If the nearest, brightest standard candle harbors anomalies, could more distant Cepheids conceal smaller ones that we simply cannot resolve? And if so, what does that mean for the galaxies whose distances and whose contribution to the cosmic expansion rate are built upon them? The timing could not have been worse. In cosmology, the so-called Hubble tension was sharpening. Measurements of the universe's expansion rate using Cepheids and supernovae produced a value higher than the one inferred from the cosmic microwave background. The gap was small but stubborn, large enough to suggest new physics or hidden systematic errors. Into that storm came the North Star, whispering that even our calibrators might be less stable than assumed. If Polaris is mismeasured, then perhaps the Hubble tension is not new physics, but an artifact of uncertain candles. For scientists, this was more than an academic puzzle. It was existential. The expansion of the universe is one of the most profound truths astronomy has revealed, and its rate of acceleration determines the fate of the cosmos. If the ruler by which it is measured wavers, then every conclusion drawn from it must tremble as well. The North Star, steady to human eyes, became a symbol of fragility in science itself. Emotionally, the shock ran deeper. Polaris had been mythologized as permanence, the axis of heaven, the celestial anchor. To find it unstable, inconsistent, almost unmeasurable, was to see constancy itself fray. Philosophers of old had pointed to the stars as proof of eternal order. Modern science now whispers that even the most trusted among them can mislead. The paradox resonated beyond data tables. It was a reminder that human certainty is a story told against a backdrop of cosmic uncertainty. By the early decades of the 21st century, the Polaris problem was no longer just a puzzle in stellar astrophysics. It was a warning bell ringing at the heart of cosmology. Scientists faced an unsettling question. If even the North Star cannot be pinned down with precision, how many of our other measurements are shadows drawn by instruments struggling against the brightness of truth? The shock had transformed into a deeper mystery. A star steady enough to guide ships across oceans, yet slippery enough to make the universe's expansion uncertain. A beacon for wanderers, yet a riddle for scientists. If Polaris defies our attempts to measure it, then what else in the cosmos waits quietly to overturn the rules we thought were certain? By the time Polaris had unsettled astronomers with its defiance of Cepheid laws, the question was no longer whether something was strange, it was how deep the strangeness ran. To answer, science turned from broad surveys to increasingly sharp tools, gathering every photon, every vibration, every whisper of data the star was willing to give. If the North Star would not yield to simple observation, then humanity would listen with finer ears. The late 20th century marked the beginning of this forensic phase. Astronomers realized that the heartbeat of Polaris could not be understood through occasional observation. It demanded continuous, long-term watching. Networks of observatories, armed with photometers and spectrographs, began recording the star's brightness night after night, year after year. These light curves became a kind of diary, showing the fading of its amplitude through the mid-1900s and the surprising resurgence in the decades that followed. Like the pulse of a patient under watch, the graphs revealed fluctuations beyond any textbook expectation. The amplitude had shrunk so low that at one point Polaris appeared nearly constant. Then, inexplicably, it stirred again, its beat louder, as though a star could change its mind. Spectroscopy gave another layer to the diary. By breaking light into its spectrum, astronomers could watch absorption lines shift back and forth as the star's surface expanded and contracted. The data revealed that Polaris's pulsation period was not merely drifting, but accelerating. changing by several seconds per year, far more rapidly than evolutionary models predicted. A star's heartbeat is supposed to change on million-year scales, not within a human lifetime. Yet Polaris's pulse seemed impatient, evolving visibly in just a few decades. More instruments were pressed into service. The Hubble Space Telescope, with its fine guidance sensors, tracked minute positional shifts. At last, astronomers managed to resolve the faint close companion, Polaris AB, separating its ultraviolet light from the glare of the giant. This was not just a technical victory, it was an unveiling of a long-suspected actor in the mystery. Polaris was not a solitary Cepheid at all, but a star entangled in a gravitational duet. Its rhythm, perhaps perturbed by its partner's unseen tug. The presence of the wider companion, Polaris B, added a third voice to the chorus. What had once been drawn in textbooks as a single steady light was, in truth, a triple system performing a complex gravitational symphony. The Gaia mission added its own pieces to the puzzle. Its astrometric precision allowed astronomers to refine parallax measurements, but even Gaia carried caveats. Very bright stars like Polaris saturated the detectors, introducing systematic errors. Researchers could see the numbers, but every result came with an asterisk. The distance still hovered uneasily between two possibilities, about 323 light-years, or closer to 430. Both values persisted in the literature, as though the universe itself refused to cast a single vote. Patterns began to emerge in the irregularities. Polaris's period change was not steady, but episodic, showing moments of rapid acceleration, then slowing. Its amplitude did not just fade and revive randomly. It seemed tied to longer cycles still poorly understood. These complexities hinted that the star's internal structure, convection zones, ionization layers, perhaps even core processes, might be more tangled than models assumed. Instead of a metronome, Polaris was more like a living organism, with rhythms layered upon rhythms, reacting to influences we could barely detect. At professional conferences, graphs of Polaris became cautionary tales. When lecturers showed the Leavitt law, the straight line relating period and luminosity, someone inevitably pointed to Polaris's misfit point. Jokes were made, but beneath them was real unease. If the nearest Cepheid refused to align, how much could we trust the distant ones, where the data were noisier and companions were invisible? The question lingered like static in every discussion of cosmic distances. Even more unsettling was the suggestion that Polaris's anomalies might not be unique. Other Cepheids, when studied with increasing precision, also revealed quirks, additional modes, irregular period changes, puzzling shifts in brightness. Perhaps Polaris was not the exception, but the first warning, the brightest example of a broader complexity hidden by distance in others. If so, the very scaffolding of the cosmic distance ladder required reinforcement, perhaps rebuilding. Through all this, the human paradox deepened. The North Star continued to shine unwavering in the night sky, guiding travelers and anchoring constellations. No observer without instruments would suspect it of anything unusual. Its light was constant enough to inspire myth, steady enough to guide explorers across oceans. Yet within observatories, graphs and spectra told another story. A star restless, unstable, slipping away from certainty. It was as though the universe maintained two versions of Polaris, the mythic beacon and the scientific riddle, and revealed them selectively, depending on how one chose to look. The investigation became a mirror. scientists realized they were not just probing a single star, but confronting the limits of measurement itself. Parallax, photometry, spectroscopy, and interferometry. Each tool told part of the story, but disagreed with the others. The search for Polaris's truth became a parable of science. Knowledge is not a set of fixed answers, but a convergence of imperfect perspectives. The North Star taught humility by refusing to give certainty, and yet the hunger for certainty did not fade. Astronomers spoke of future missions, more precise instruments, more sensitive detectors. Perhaps one day a telescope would capture Polaris without bias, separating companions, resolving its parallax beyond doubt, freezing its pulse into clarity. Until then, the North Star remained what it had become, the most measured and least measurable star in the sky. The diary of light and data had brought us here, a Cepheid that changed its heartbeat within human lifetimes, companions that pulled invisibly at its rhythm, distances that shifted with every new telescope. Polaris stood as both a triumph of observation and a rebuke to theory. If Polaris can visibly evolve within decades, are we witnessing stellar evolution in real time? If companions distort their pulse, what unseen systems distort the Cepheids on which our cosmology rests? And if the very ruler of the distance ladder wavers, then how steady is the ladder at all? The closer astronomers pressed their instruments to Polaris, the more the star seemed to resist. If the North Star had once been a symbol of constancy, the new millennium revealed it as a master of disguise, hiding truths in plain sight. Long-term monitoring campaigns expanded across the globe, as if humanity had resolved to keep an eternal vigil. No single observatory could catch every flicker, so networks of telescopes coordinated to create continuous coverage, building an unbroken timeline of light. From these campaigns came revelations that unsettled even seasoned astronomers. The pulsation period, already known to drift, was shown to be accelerating, changing on timescales never before associated with Cepheids. Instead of the slow, graceful evolution expected of a yellow supergiant, Polaris appeared restless, its internal equilibrium disturbed. The light curves, once expected to be steady rhythms etched in the sky, became records of a star in transition, as if it were caught mid-sentence in the language of stellar evolution. Interferometry joined the arsenal. By linking multiple telescopes to act as one giant instrument, astronomers attempted to measure Polaris's angular diameter directly. The results were remarkable. The star's apparent size shifted slightly as it pulsated, a visible breathing motion captured across the void. When converted into physical units, the measurements implied a radius larger than expected for a Cepheid of its period. This discrepancy compounded the confusion. Either the models of Cepheid structure needed revision, or Polaris was hiding some extraordinary peculiarity within its atmosphere. Spectroscopic surveys revealed further layers of complexity. Beyond the principal pulsation mode, subtle signals hinted at secondary oscillations, faint ripples over the dominant beat. Some researchers interpreted these as evidence of non-radial modes, vibrations that shook the star in complex patterns, rather than simple expansion and contraction. Cepheids were not supposed to behave this way, at least not the classical ones used as standard candles. Polaris seemed determined to exhibit every exception possible. Meanwhile, its companions continued to complicate interpretation. The dwarf Polaris AB was close enough to stir gravitational effects in the giant's pulsation and orbital motion. Precise measurements of its orbit promised, in theory, to pin down the system's distance and mass distribution. yet the calculations never converged neatly. Some datasets place the dwarf's orbit at one inclination, others at another. Small errors are magnified into large uncertainties. Even in binary dynamics, Polaris blurred the numbers. The wider companion, Polaris B, long regarded as a passive background object, emerged as a further wrinkle when its own properties were compared against models of stellar populations. The system was not only unusual in its Cepheid, but in its family history. The more carefully scientists looked, the more Polaris turned into a hall of mirrors. Models of stellar interiors suggested one set of values for its age. Orbital mechanics suggested another. Its brightness hinted at a third. Some estimates placed it at 50 million years, others at nearly 100 million. For a star so central to myth and science alike, this uncertainty bordered on the absurd. How could humanity measure galaxies billions of light-years away, yet fail to fix the age of the North Star? These anomalies pressed a deeper unease. Cepheids were supposed to be simple tools, pulsating, luminous, predictable. They had powered Edwin Hubble's discovery of an expanding universe, and they underpinned the modern debate over cosmic acceleration. If Polaris revealed hidden layers of complexity, perhaps Cepheids were never as simple as scientists had assumed. Perhaps the very reliability of Leavitt's law, though broadly correct, masked subtleties that only the brightest, closest example could expose. The philosophical weight grew heavy. Imagine for a moment a sailor in the 15th century steering his vessel across unknown seas, Polaris unwavering above the mast. For him, the North Star was the one certainty in a world of shifting tides and unknown horizons. Now, centuries later, astronomers with spaceborne observatories, the most advanced eyes humanity has ever built, find that same star refusing to reveal its distance, its pulse, even its age. The paradox cuts deep. The symbol of certainty is the embodiment of uncertainty. And yet, this very resistance is what makes Polaris invaluable. By refusing to fit the mold, the North Star forces science to sharpen its tools, refine its theories, and question its assumptions. Each anomaly is not a dead end, but an invitation, a reminder that progress is born not from what is easy to measure, but from what resists measurement. Polaris stands as the most difficult Cepheid because it is also the most instructive. But the tension between certainty and uncertainty persists. As interferometers record its breathing, as spectra reveal hidden ripples, as satellites debate its distance, the fundamental questions remain unresolved. Is Polaris's misbehavior simply the quirk of a star caught in an unusual evolutionary phase? Are its companions the unseen hands that distort its pulse? Or does the North Star hint at flaws in the very framework astronomers use to weigh and measure the universe? The deeper the investigation, the sharper the mystery becomes. Instead of converging on clarity, the evidence spreads outward like ripples on dark water. Every measurement confirms that something is wrong, but nothing confirms exactly what. If the North Star, the brightest Cepheid, the nearest, the most measured, resists comprehension, what does that mean for the billions of stars too far away to study in such detail? By the time the 21st century unfolded, what began as a curious inconsistency in Polaris had escalated into something far larger. The North Star no longer represented just a riddle in stellar astrophysics. It was becoming a mirror for the limits of human certainty itself. Each attempt to resolve its contradictions only widened them. Each layer of observation revealed another fault line. What should have been a solved puzzle, the nearest, brightest, and most accessible Cepheid variable, was mutating into a crisis of confidence that reached from the interiors of stars to the edges of the observable universe. Polaris's pulsation, once expected to be a predictable metronome, had become a spectacle of defiance. Its period, the heartbeat of its light, continued to drift at a pace faster than stellar evolution models could justify. This was no minor quirk. Cepheid pulsations are the cornerstones of the period luminosity law. If Polaris bends the rhythm, then the entire calibration of that law is shaken. For decades, astronomers reassured themselves that the anomaly was local, confined to one peculiar star. But as data improved, faint irregularities began to surface in other Cepheids as well. Polaris was not simply misbehaving, it was sounding an alarm for the whole category. The revival of its pulsation amplitude only deepened the unease. A star that nearly silenced its variability had inexplicably begun to pulse again, as though rebelling against its own decline. Scientists offered explanations: changes in stellar structure, convective reshuffling, or interactions with a companion, but none fit neatly. The return of the amplitude was not only unexpected, it was unprecedented. In every Cepheid textbook, stars were meant to fade along smooth, predictable trajectories. Polaris had torn a page from that book and rewritten it with a flourish no theory could yet explain. The distance dilemma, meanwhile, refused to yield. Gaia, Hipparcos, and Hubble stood like three witnesses giving three testimonies. Each pointed to a slightly different version of reality, and none could be fully dismissed. The range between approximately 323 and 433 light-years may seem small on human scales, but on cosmic scales, it was catastrophic, because Cepheids are used to measure galaxies millions of light-years away. An error in Polaris's calibration reverberated outward like a magnified echo. The entire cosmic distance ladder, from parallax to Cepheids to supernovae to the expansion of the universe, trembled at its base. The timing was cruel. Cosmologists were already embroiled in the so-called Hubble tension, where local measurements of the universe's expansion disagreed with values derived from the cosmic microwave background. Into this storm stepped Polaris, hinting that perhaps the first rung of the distance ladder was less stable than assumed. The star that once guided explorers across oceans was now threatening to disorient the explorers of the cosmos itself. The companions of Polaris added to the escalation, not relief. The direct imaging of Polaris AB confirmed the system's complexity, but disentangling its gravitational effects on the Cepheid's pulsation proved maddening. Some simulations suggested the dwarf companion was altering the primary's oscillations subtly but significantly. Others found the effects too small. The wider companion, Polaris B, raised still more questions about the system's formation history. Was this a primordial triple, or the result of captures and interactions? The truth matters because a star's origin shapes its evolution, and Polaris's peculiarities might be the scars of a turbulent birth. Spectroscopy revealed yet another twist. Beyond the dominant four-day rhythm, faint signatures of irregular oscillations crept into the data. Some astrophysicists argued these were non-radial pulsation modes, vibrations echoing through the star in complex geometries. If true, Polaris was not simply bending Cepheid laws, but exposing hidden dimensions within them. What had been treated as a simple pendulum was closer to a choir of clashing notes, each revealing new layers of stellar physics. The escalation was not just technical, but philosophical. For centuries, Polaris had symbolized permanence. Ancient cultures enshrined it as the axis of heaven, the fixed point around which all others turned. It was the emblem of orientation, certainty, and homecoming. But to modern science, it had become the opposite, the most unstable of constants, a fixed point that refused to be fixed. The paradox was cruel and poetic. Humanity's compass star was becoming its cosmic enigma. In conferences and papers, the tone shifted. No longer did scientists speak of solving Polaris quickly. They began to admit that it might remain ambiguous for decades. The best instruments available, space telescopes, interferometers, and long baseline spectrographs, had delivered not closure, but deeper puzzles. The North Star was humbling the very science that once believed it could chart the cosmos with certainty. And yet escalation breeds revelation. By refusing to conform, Polaris forces astronomy to sharpen its edges. Every contradiction spurs new technology, new models, new ways of seeing. In its defiance, the star has become both problem and teacher. Like a difficult text that resists interpretation, Polaris stretches human thought until it reaches its limits. But the mystery only grows sharper. The next phase of investigation would probe even more deeply. The attempts to measure Polaris's precise diameter, the search for hidden cycles in its pulsation, and the unsettling possibility that the North Star is not just an anomaly, but a warning that the universe itself may be stranger than the rules we have written for it. If the very star that has anchored human direction refuses to anchor science, what does that reveal about the nature of truth in the cosmos? The investigation of Polaris had become less about answers and more about confronting the stubbornness of the cosmos. With each instrument pointed at the star, the contradictions multiplied. Astronomers turned to interferometry, linking distant telescopes to measure the star's apparent diameter with astonishing precision. The results showed a star that breathed in and out across its pulsation cycle, its size changing by measurable amounts. But when those diameters were compared to models, they revealed a radius larger than expected. Polaris was not only a Cepheid that changed its rhythm, it was one that seemed to wear a body bigger than theory allowed. Long-term monitoring added more texture. Night after night, observatories captured light curves that looked less like the smooth waves of a predictable star and more like the erratic signals of something unsettled within. At times, its variability dulled. At times, it surged. And across the decades, it shifted in ways that hinted at deeper processes playing out beneath the surface. The pattern suggested that the star was not simply a variable in transition, but perhaps a living record of stellar evolution caught in motion, a kind of time-lapse happening on a cosmic scale short enough to be seen within a human lifetime. Spectroscopy added its own surprises. Absorption lines swayed not just with the expected pulsation, but with hints of additional oscillations. Some scientists argued these were non-radial modes, patterns of vibration crossing the star at odd angles, overlapping like ripples colliding on water. Cepheids were never meant to sing this kind of complex harmony, yet Polaris did, challenging the simplicity of the laws astronomers had written for it. The companions, once thought minor players, became central to the drama. Polaris Ab, the faint dwarf hugging close to the giant, made its presence felt in orbital tugs and spectral fingerprints. Its gravity pulled at the system's balance, complicating every calculation of mass and distance. Polaris B, the wider companion, raised new questions about the history of the system itself. Was this a triple system born together, or a family pieced together through cosmic capture. The truth mattered, for the story of a star's birth can echo in its heartbeat millions of years later. And still the distance problem lingered like a shadow. Hipparchus, Hubble, Gaia, each told a slightly different story, and none agreed fully with the physics of pulsation. A star less important might have been left unresolved, but Polaris was the linchpin of an entire framework, the point on which galaxies and even the expansion of the universe were measured. Every uncertainty in its distance became an uncertainty in the scale of the cosmos. For cosmologists, this escalation was more than inconvenient. It threatened the reliability of the distance ladder itself. At the very moment when the Hubble tension was splitting the field, Polaris refused to settle into clarity. Was the universe expanding faster than expected, hinting at new physics? Or were the measurements flawed from the first rung of the ladder? Polaris stood at that rung, refusing to choose a side. The philosophical weight pressed heavily. A star that guided travelers home could not guide science to agreement. For ancient sailors, Polaris was a compass point in an endless sea. For astronomers, it had become a symbol of the sea itself, vast, restless, ungraspable. Its light reached Earth unchanged, yet the meaning of that light fractured into arguments and uncertainties. Still, its resistance was a kind of gift. By refusing to conform, Polaris demanded sharper instruments, deeper theories, more humility. It reminded astronomers that nature does not owe simplicity to human thought. Every irregular heartbeat, every stubborn parallax, every conflicting measurement was a lesson written in starlight, that the cosmos is stranger, subtler, and less obedient than the equations we write for it. Polaris burned on in the northern sky, steady for every human eye that found direction in it, yet shifting under the scrutiny of science. The paradox deepened with every observation, until the star seemed less like a Cepheid and more like a messenger, carrying a quiet warning that certainty in the universe is always provisional. The escalation had turned one star into a symbol of doubt, and doubt in science is never the end. It is the beginning. Polaris had revealed itself as more than a misbehaving Cepheid. It had become a star that stretched the patience of theory itself. Every new dataset suggested that what astronomers thought was solid ground was in fact shifting beneath their feet. The deeper they dug, the more the mystery refused to shrink. Instead, it grew larger, spreading its weight into every corner of stellar physics and cosmology. The star's pulsation did not simply drift, it defied prediction. One year, its period shortened at a pace far beyond expectations. Another year, it seemed to slow again. The change was not linear, but erratic, like a pendulum swinging through invisible currents. A Cepheid's period should be a signature of its internal structure, a guide to its age and mass. But Polaris was a signature that blurred as soon as it was written, as though the star itself were rewriting its autobiography while astronomers tried to read it. The amplitude of its heartbeat, too, refused to follow the rules. The near collapse of its variability in the 20th century had shaken confidence, but the revival was an even deeper shock. Stars are not supposed to recover their pulses after decline. The physics that drive Cepheids is not reversible in that way. Yet Polaris surged again, a rhythm reborn, as if something inside had reignited. What internal fire had turned back time within the star? What mechanism had defied the natural cooling of its oscillations? The questions swirled without answers, leaving only the unsettling recognition that Polaris was teaching us how little we knew of stellar interiors. The companions made the mystery even denser. The close dwarf AB traced an orbit that shifted Polaris's center of gravity, introducing tiny distortions into every attempt to measure its distance or its pulse. The wider companion B remained a quiet sentinel, but its very presence forced astronomers to rethink the system's origin. How could a triple system like this have formed? Was the Cepheid altered by interactions early in its life, forced onto a path that no solitary star could follow? If so, then perhaps Polaris was not just an anomaly, but evidence of stellar histories that our models never accounted for. Interferometric observations captured its surface swelling and contracting, emotions so delicate it could be traced across the light years. But when those sizes were compared to theory, the numbers strained against expectations. The radius was too large, the pulsation too irregular, the mass too hard to pin down. Even the chemical composition of its atmosphere, teased out by high-resolution spectra, raised puzzles, elements mixed in patterns that hinted at unusual evolutionary pathways, as if the star had burned through its life stages out of order. For cosmologists, the implications were unsettling. Cepheids were meant to be cosmic lighthouses, regular enough to guide our measurements of the expansion of the universe. But if the closest, brightest example was riddled with anomalies, how many uncertainties lay hidden in the faint Cepheids used to measure galaxies millions of light-years away? If Polaris could evolve this dramatically within decades, then how stable were the assumptions underlying the Hubble constant itself? The echo of this doubt reached far beyond one star, touching the fate of the cosmos. And yet, within the scientific unease, there was awe. Polaris was no longer just the compass star of navigators or the textbook Cepheid of astronomers. It had become something more profound, a star caught in the act of change, a living experiment in stellar evolution unfolding within the span of human observation. Most stars live and die on timescales too long to witness. Polaris had offered us a rare exception, a window into transformation as it happens. Not as it is reconstructed after the fact. Its light became both warning and gift. Warning because it unsettled the cosmic ladder. Gift because it forced astronomers to confront their assumptions, to refine their instruments, to see more clearly. The North Star was no longer a fixed point in the heavens. It was a shifting mirror, showing science both its power and its fragility. And as it burned, constant to the naked eye, erratic under the scrutiny of telescopes, a deeper realization settled in. The mystery of Polaris was not confined to a single star. It was a reflection of the universe itself, vast, complex, and forever resisting the cages of certainty. The mystery of Polaris did not recede as astronomers layered observation upon observation. It only widened, spilling into places where it had no business reaching. What should have been a local puzzle, a nearby Cepheid with a few irregularities, was beginning to cast shadows over the entire field of cosmology. The deeper scientists looked, the more Polaris revealed itself as a paradox that could not be neatly contained. Efforts to refine its distance continued, yet none achieved the finality hoped for. Gaia's updated data improved parallax measurements for countless stars, but Polaris remained burdened with caveats. It was simply too bright, too complex, too entangled with companions for easy resolution. Each release sparked debate. Had the star finally been pinned down, or were the numbers still corrupted by systematics? The arguments replayed in conference halls and journals. Unresolved year after year, Polaris seemed to defy not only distance, but agreement itself, a celestial provocateur keeping astronomers at odds. Meanwhile, the light curve stretched into decades of records, and their story grew stranger. Instead of stabilizing, Polaris's heartbeat revealed long-term cycles, unexplained modulations layered atop its 4-day pulse. These were not random noise, but patterns, subtle and insistent, hinting at processes beyond the standard Cepheid mechanism. Some researchers speculated about magnetic fields deep within the star, hidden structures that interfered with the flow of energy. Others suggested complex coupling between the star's pulsation and its rotation, forces locked in a struggle beneath its surface. None of these theories fully explained the revival of its amplitude or the erratic shifts in period. Polaris remained a patient teacher of uncertainty. Interferometric campaigns pressed onward, tracing their radius changes with increasing precision. Each dataset confirmed the star's breathing, yet the derived size continued to stretch against theoretical expectations. Polaris's radius seemed inflated, as if its envelope were swollen beyond what models could predict. Some argued this pointed to mass loss, powerful stellar winds blowing away material and altering the outer layers. If true, Polaris was shedding itself into space in a way that made its structure transient, unstable. Such a scenario turned the star into a symbol of impermanence, even as it played the role of permanence for the human eye. The companions never ceased to complicate matters. Polaris AB, tiny but insistent, orbited in ways that blurred every attempt at clarity. Its tug altered the primary star's apparent motion, injecting uncertainty into the very parallax used to judge distance. Polaris B remained an enigmatic participant, stable in the sky, yet bound to the system in ways that hinted at a turbulent history. Astronomers wondered if the peculiarities of Polaris AA, the Cepheid itself, were partly the result of gravitational interactions long ago, scars of a violent past written into its present light. At the heart of the mystery was not only data, but doubt. The Hubble tension, the clash between two different measurements of the universe's expansion rate, loomed like a storm cloud over cosmology. In this debate, Cepheids were central, and Polaris was the most important Cepheid of all. Every irregularity in its behavior casts a shadow over the distance ladder. Was the expansion rate truly higher, demanding new physics? Or was Polaris and Cepheids like it, misleading us with complexities we had not accounted for? The star refused to take a side, instead deepening the unease by reminding us how fragile the foundations of our knowledge could be. Emotionally, Polaris became more than a star. It became a contradiction that spoke to the human condition. To the naked eye, it had not changed in recorded history. It was the compass of explorers, the steady flame above the northern horizon. To science, it was a shifting, unstable entity, as volatile as it was luminous. The paradox struck deep. The very symbol of direction was also the embodiment of uncertainty. It was a reminder that certainty itself is an illusion, a human story written over a cosmic page that will not hold still. And yet, in its refusal to be simple, Polaris offered something profound. It showed that mystery is not a failure of science, but its essence. The unanswered questions are the ones that keep observation alive, keep instruments pointed upward, keep imagination restless. Polaris, by slipping out of our grasp, ensures that we continue to reach. In its contradictions lies the very fuel of discovery. As the data mount and the theories falter, the mystery of Polaris does not weaken. It expands, touching cosmology, stellar physics, and even philosophy. A single star, once thought to be the most reliable of all, has become the most elusive. Its light remains constant, but its meaning fractures, splitting into truths that cannot be reconciled. The deeper scientists look, the more Polaris appears less like a star to be solved and more like a riddle to be lived with. A permanent reminder that the universe is larger than our categories, stranger than our theories, and more patient than our pursuit of it. The mystery of Polaris could not rest forever in the realm of description. Observation had revealed the contradictions. A Cepheid that changed its rhythm too quickly, a heartbeat that nearly vanished and then revived, companions that blurred the measurements, distances that refused to agree. The time came when astronomers had to reach beyond the data and attempt to explain. Theories began to gather like constellations around the North Star, each hoping to capture its elusive truth. Yet, like starlight scattered in a prism, no single explanation emerged whole. The first line of speculation pointed inward, to the star itself. Perhaps Polaris was simply living through a rare evolutionary phase, caught at a transitional moment as it crossed the instability strip of the Hertzsprung-Russell diagram. Cepheids are known to pass through this region multiple times in their lifetimes, swelling and contracting as they burn different fuels in their cores. If Polaris were on a second or even third crossing, its pulsation could appear unstable, its period could change more rapid than usual. The revival of its amplitude might reflect the star's structure reconfiguring itself, helium ionization zones shifting deeper into the envelope, reigniting the oscillations. But models struggled to match the precise rate of change, leaving the theory plausible but incomplete. Other astrophysicists turned to the companions for answers. The close dwarf Polaris AB could be exerting gravitational influence, subtly disturbing the Cepheid's rhythm. Orbital interactions might alter the balance of forces within the star, producing irregularities in its pulse. Some even suggested tidal forces, though the distance between the two stars made this effect weak at best. Still, the very act of being part of a multiple system introduced complexities that Cepheid models rarely account for. A textbook Cepheid might never truly exist. Instead, each Cepheid might carry scars of its environment, companions writing their signatures into the light curves we assume are pure. A third speculation arose from stellar physics itself. Cepheids pulsate because layers of ionized helium trap and release heat, a kind of cosmic engine known as the Kappa mechanism. But this mechanism can be modulated by other processes: convective turbulence rising from deep within, rotation altering energy flow, or magnetic fields threading the stellar envelope. Some researchers propose that Polaris's revival in amplitude might be due to a shift in these internal dynamics. Perhaps convection grew stronger or weaker, tipping the balance of energy. Others considered the role of mass loss, with stellar winds altering the outer layers and feeding back into the pulsation cycle. Each explanation carried fragments of truth, but none stitched the fragments into a seamless whole. Beyond the stellar details lay larger cosmological concerns. If Polaris defied calibration, then Cepheids as a class might harbor hidden instabilities. Astronomers began to wonder, could this be part of the reason for the tension in the Hubble constant? Local measurements of cosmic expansion, built upon Cepheid distances, consistently yielded higher values than those inferred from the cosmic microwave background. Perhaps the discrepancy was not new physics, but hidden uncertainties in the stars themselves. Polaris, the nearest and brightest Cepheid, might be the clue or the warning that Cepheids are less uniform than once believed. If so, the star was whispering a subtle message. The ladder of distance we climb into the universe rests on steps that may not all be level. Yet the allure of new physics could not be ignored. Some speculated that if Cepheids like Polaris are truly anomalous, then perhaps the universe itself is stranger than our equations allow. Maybe the Hubble tension is real, a sign of dark energy evolving or new particles influencing cosmic structure. In that case, Polaris is not misleading us. It is forcing us to confront the limitations of the models we impose on the cosmos. Its refusal to fit would not be an error, but a beacon pointing toward a deeper truth. The speculative landscape grew wide. Papers debated scenarios of resonance, where multiple pulsation modes interfere, producing the irregular patterns observed. Others considered rotation-induced mixing, altering the composition of the core and thereby the pulse. Some ventured that unseen companions, too faint to detect, might be adding further disturbances. The North Star became less a single mystery and more a gallery of possible explanations, each partial, each contested. And through it all, the paradox endured. Polaris still guided sailors, still marked the axis of Earth's rotation, still appeared steady to every human eye that looked up. Yet, in the language of science, it was a storm of contradictions, pulling astronomers into speculation after speculation, never allowing certainty. Perhaps that was the deeper lesson. Theories are not walls of stone, but scaffolds of wood, built to reach a truth that may forever recede. Polaris reminded astronomers that explanation is always provisional, always fragile, always waiting to be overturned. It was less a puzzle to be solved than a dialogue between star and scientist, an ongoing conversation written in flickering light. The first half of that conversation had now been laid out. Models of stellar evolution stretched to their limits, companions interrogated for hidden effects, physical processes reimagined, cosmological implications debated. None gave the final answer. All deepened the riddle. Speculation around Polaris multiplied not because scientists lacked discipline, but because the star refused to be captured by a single narrative. It was as though the North Star had become a prism, splitting theory into many beams, each illuminating part of the truth while leaving shadows in the corners. Some astronomers turned to resonance models, suggesting that Polaris's irregularities might come from interference between its pulsation modes. Cepheids usually throb in a fundamental rhythm, but higher overtones can sometimes emerge, faint echoes that complicate the song. If Polaris's fundamental and overtone modes interacted, they might produce the erratic amplitude changes observed across the 20th century. The near collapse of its variability could have been a destructive interference, with two beats nearly canceling out, followed decades later by their resurgence in constructive harmony. It was a beautiful possibility, elegant in its imagery, but difficult to prove. The data hinted, but did not confirm. Others emphasized the role of mass loss. Cepheids are not static objects. They bleed material into space through powerful winds. If Polaris has been shedding its outer layers more rapidly than expected, the process could alter its envelope structure, destabilizing its pulsations. Such an explanation offered a link to its inflated radius and revived variability, a star reshaping itself as it peels away. Observations in the ultraviolet and infrared revealed circumstellar material that supported this view, but quantifying the exact effect on its heartbeat remained elusive. Rotation entered the debate as well. Rapidly rotating stars can mix their interiors, dragging fresh hydrogen into the core and redistributing heavy elements throughout the envelope. This mixing alters the star's evolutionary path, potentially explaining why Polaris appears younger or older, depending on which model is used. If rotation has shaped its life, then perhaps the Cepheid laws derived from non-rotating models are incomplete. Polaris might be telling us that stars cannot be understood in isolation from their spin, that time itself flows differently for those who whirl as they burn. Some of the boldest speculations reached into the domain of magnetism. Magnetic fields, though difficult to detect in such luminous giants, can act as hidden architects within stellar envelopes, channeling flows of plasma, damping oscillations, or amplifying them unpredictably. A magnetic Polaris would be a far more complicated star than textbooks describe. Its variability, a kind of coded message written in field lines. To many, the idea was tempting, but without clear observational evidence, it hovered at the edge of plausibility, a theory waiting for the right instrument to confirm or deny it. The companions continued to haunt every explanation. The faint dwarf, Polaris AB, exerted its pull in ways too small to dismiss and too large to ignore. Even the wide companion, Polaris B, became part of the speculation. Some researchers propose that interactions in the star's youth, close passes, mass exchanges, perhaps even the capture of one component, could have set Polaris on its peculiar course. If so, the mystery was not in its present alone, but in its past, a cosmic history written in gravitational scars. All of these ideas swirled into a larger debate that stretched beyond the North Star. If Cepheids could be this complicated, could we truly rely on them as standard candles for cosmology? Or were we projecting simplicity onto complexity, trusting rulers that bent even as we use them to measure the universe? This question bled into the crisis of the Hubble tension, where different methods of gauging cosmic expansion clashed. To some, Polaris symbolized the fragility of local measurements, the possibility that errors in Cepheid calibration might explain the discrepancy. To others, the persistence of the tension suggested the opposite, that new physics weighted beyond our understanding, and that Polaris was simply a reminder of how messy the cosmos looks up close. In this way, the star became more than an astrophysical subject. It became a philosophical mirror. Its refusal to settle into one explanation reminded humanity that the universe does not owe us clarity. Theories are scaffolds, built to approximate reality, and sometimes reality pushes back. Polaris showed that even the brightest star in the northern sky can evade our definitions, forcing us to accept mystery not as failure, but as truth in progress. The speculations continue today, each adding nuance, none closing the case. Perhaps Polaris is a transitional Cepheid caught mid-passage. Perhaps it is warped by companions, rotation, or magnetism. Perhaps it is all of these at once, a confluence of forces converging in one star. Whatever the answer, the North Star remains what it has always been, a guide, not in the sense of a compass pointing north, but in the sense of a puzzle guiding us deeper into humility, deeper into curiosity, deeper into the recognition that our instruments measure not only the stars, but also the limits of our own understanding. Polaris burns on, steady to the eye, restless under the lens. And in that paradox lies its greatest gift, a reminder that science is not a quest for finality, but a journey through endless approximation, where every answer is the threshold of another question. The refusal of Polaris to yield its truth did not silence astronomers. Instead, it galvanized them, pulling ever more powerful instruments into its orbit. The North Star, uncooperative as it was, had become a testing ground for the very limits of observation. If science could unravel Polaris, then perhaps it could measure anything. If it could not, then the star would remain a wound in the certainty of the cosmos. The Hubble Space Telescope stood at the forefront of this effort. With its fine guidance sensors, instruments designed to hold the telescope steady on distant targets, Hubble became one of the few tools precise enough to attempt parallax on a star as bright as Polaris. The measurements it delivered offered a distance larger than Hipparchus had claimed, restoring some faith in the traditional picture of Cepheid luminosity. Yet even here, uncertainties lingered. Polaris's companions tugged at its motion, and Hubble's instruments were never designed to untangle such complications. What should have been a clear resolution was instead another round in the long debate. On the ground, interferometry offered another weapon. By linking telescopes across baselines miles apart, astronomers synthesized apertures large enough to resolve the swelling and shrinking of Polaris's disk as it pulsed. These measurements confirmed that the star's radius was not static, but breathing. In principle, this allowed researchers to apply the Bode-Wesselink method, combining changes in angular diameter with radial velocity shifts to calculate distance directly. In practice, the method struggled. The numbers wavered depending on assumptions about limb darkening, atmospheric dynamics, and the influence of companions. Each refinement added precision and doubt in equal measure. Spectroscopy continued its vigil. High-resolution spectrographs monitored Polaris's absorption lines, tracing the rise and fall of its surface layers as the star inhaled and exhaled light. These campaigns confirmed the rapid drift in pulsation period, capturing it in real time across decades. Some teams even detected faint additional oscillations, whispers of secondary modes that complicated the star's song. Data poured in, yet every dataset raised as many questions as it answered. Polaris seemed determined to give just enough clarity to sustain hope, just enough ambiguity to deny closure. The Gaia mission loomed large in this chapter. Tasked with mapping the Milky Way in 3 dimensions, Gaia was built to measure parallaxes with unprecedented precision. For millions of stars, it succeeded. But for the very brightest, including Polaris, its detectors strained under saturation. Sophisticated calibrations could correct most cases, but for Polaris, the results came stamped with warnings. Even the finest astrometric machine humanity had ever built could not lock down the North Star. In the catalogs, their numbers were there, but like text written in fading ink, they demanded caution beyond direct measurement. Polaris drove advances in modeling. Computer simulations of stellar interiors grew more sophisticated, incorporating rotation, convection, and mass loss in ways unimagined a generation earlier. Some of these models reproduced fragments of Polaris's behavior, such as its rapid period change or its revived amplitude. None captured the full picture. The more realistic the simulations became, the clearer it was that reality still outpaced them. Polaris resisted not only observation, but imagination. In parallel, ultraviolet and X-ray instruments searched for evidence of stellar winds, trying to catch mass loss in the act. Infrared surveys scanned for circumstellar dust, remnants of material shed into the surrounding space. These campaigns found hints that Polaris was indeed losing mass, surrounding itself in a faint halo of its own making. Yet, the connection to its pulsation irregularities remained speculative. Was mass loss the cause, or another symptom of deeper instability? What made Defies remarkable was not only the instruments themselves, but the persistence behind them. For more than a century, Polaris had been under scrutiny, its light curves stretching across generations. Children born when its amplitude first began to decline had grown old by the time it revived. The star had become a multi-generational project, a riddle passed down through the hands of successive astronomers. It stood as a reminder that science is not just a matter of discovery, but of patience, of watching long enough to see what the universe chooses to reveal. Yet, patience did not erase the paradox. Despite every tool, every model, every dataset, Polaris remained a star of contradictions. Its period drifted too fast. Its amplitude defied prediction. Its distance split the instruments meant to measure it. Its companions blurred its light. Every advance in technology sharpened the image, but left the meaning blurred. The closer humanity came, the farther certainty seemed to recede. And still, Polaris shone on, steady for the human eye, elusive under the scientist's gaze. It became a kind of cosmic riddle carved into the night sky, daring humanity to solve it, while whispering that perhaps it could not be solved at all. The tools had grown sharper, the testing had grown relentless, but the mystery had only deepened. The search for clarity pressed on, carried by instruments old and new, each attempting to wrest a final truth from the North Star. If Polaris would not settle into theory, then theory would bend itself around Polaris, guided by the light of ever more advanced technology. Astronomers expanded long-term monitoring into global collaborations. Networks of observatories tracked Polaris night after night, creating an unbroken chain of data across continents. With these records, they traced subtle shifts invisible to single campaigns, small wiggles in the pulsation period, faint irregularities in brightness, long-term cycles buried beneath the main rhythm. These archives, stretching across decades, revealed a star that refused stasis. Its pulse seemed to write a story of constant revision, as though evolution itself had quickened within its core. Interferometric arrays grew bolder. Facilities like the Chara Array and the Very Large Telescope Interferometer linked telescopes across vast distances, capturing Polaris's diameter changes with unprecedented resolution. They measured the rise and fall of its surface, watching its atmosphere breathe in light years made small. Yet even these triumphs brought paradox. The star's size, carefully calculated, remained inconsistent with models. It appeared larger than theory allowed, forcing astronomers to confront the limits of their equations. Was the Cepheid framework incomplete, or was Polaris alone a misfit? The instruments could show the motion, but not the meaning. Spectroscopy pushed deeper, dissecting Polaris's light with razor-thin precision. Subtle shifts in spectral lines revealed complexities in the star's velocity fields, suggesting turbulence far greater than expected. Some patterns hinted at non-radial oscillations, strange ripples cutting diagonally through the star. Others pointed to chemical peculiarities, evidence of mixing processes, or past mass loss that had reshaped its atmosphere. Every finding seemed both a revelation and a rebuke, confirming detail while undermining simplicity. Meanwhile, Polaris became a test case for data fusion. Astronomers combined results from parallax, interferometry, spectroscopy, and pulsation models, weaving them together into hybrid estimates. But the synthesis proved unstable. Distances disagreed, masses diverged, radii conflicted. Like a puzzle assembled from mismatched pieces, the picture could never quite align. Some scientists suggested that Polaris was not merely unusual, but unique, a star at the crossroads of multiple rare conditions, producing an object unlikely to be mirrored elsewhere. Others countered that its anomalies might point to hidden complexities in all Cepheids, concealed in those too faint or too far to study with such care. Gaia continued to feed its data into the debate, its precision unmatched, but its cautionary notes unavoidable. For Polaris, the catalogs remained clouded by the star's brightness, its multiplicity, and its irregularities. The very instrument built to settle stellar distances could not tame the North Star. The irony was sharp. The flagship astrometric mission of the modern era could map billions of stars, but not the one humanity knew best. Amid the frustration, there was recognition that Polaris was more than an obstacle. It had become a benchmark for testing the boundaries of technology itself. Every attempt to measure it forced engineers to refine detectors, calibrate instruments, and push methods further. The star's resistance spurred growth, a kind of cosmic training ground where tools proved themselves against the hardest possible target. In resisting certainty, Polaris gave science its sharpest edge. Beyond instruments, the star also became a symbol of the future. Proposed space missions, imagined with even greater precision than Gaia, often included Polaris in their lists of targets. New interferometers, designed to stretch across orbits or even positions in space, promised to resolve their companions more clearly, to pin their parallax without ambiguity. Polaris stood as both a challenge and a prize, the riddle that would test every next generation of astronomy. And yet, beneath the excitement of tools and testing, the philosophical paradox remained. The North Star still marked direction for every traveler who lifted their eyes to the sky. To them it was unchanging, eternal, a comfort in the darkness. To science, it was the most measured star that refused to be measured, the most studied light that refused to be understood. It stood as a lesson that no instrument, however precise, can erase the mystery woven into the fabric of reality. In the end, the testing revealed as much about humanity as it did about the star. It showed a species unwilling to accept ignorance, relentless in its pursuit, willing to devote centuries of observation to a single object of light. It showed that our greatest tools are not telescopes or satellites, but patience and persistence. Polaris resisted, but humanity endured, turning each failure into another attempt, another refinement, another fragment of understanding. The story of scientific tools aimed at the North Star is not one of conquest, but of humility. For every triumph, a resolved companion, a measured radius, a traced pulsation, there remains a deeper ambiguity. Polaris does not give up its truth easily. Perhaps it never will. Perhaps that is its lesson, that science advances not by solving every riddle, but by living within them, learning to navigate uncertainty as sailors once navigated seas by its light. The mystery of Polaris had grown far beyond astrophysics. What began as the study of a Cepheid variable had turned into something deeper, something that reached into philosophy and the human heart. The North Star was no longer just a stellar anomaly. It had become a paradox, steady to the eye, unstable to the telescope, trusted by history, mistrusted by science, a compass for sailors, a riddle for astronomers. For ancient cultures, Polaris was more than light. It was permanence in a world of change. Farmers in the Fertile Crescent looked to its fixed position to chart their seasons. Navigators on the open seas held their course by it, placing their lives in its consistency. Poets made it a symbol of loyalty, of love that does not drift. For millennia, Polaris was the sky's guarantee that something in the universe remained still. To discover that this very star hides turbulence and uncertainty is to discover something unsettling about certainty itself. Science had stripped away the veil of myth, but it had not replaced it with clarity. Instead, it revealed a truth both humbling and beautiful, that stability is an illusion born of distance. From far away, Polaris shines unchanging. From close, it flickers, shifts, evolves, betrays its own contradictions. Perhaps this is not failure, but revelation. The universe does not give us permanence. It gives us change, hidden beneath the appearances we trust. The paradox presses against the human desire for order. We want the stars to be reliable, the cosmos to be calculable, the universe to be a clock we can wind. Polaris reminds us that the universe is not a clock, but a storm, patient on the surface, restless underneath. The North Star has become the mirror of our limits. It reflects our yearning for certainty, and it shows us that certainty is a story we tell ourselves to feel safe. And yet, in that humility lies wonder. To know that even the closest Cepheid cannot be measured with precision is not despair. It is awe. It means that the universe is greater than our grasp, that mystery is not something that waits at the edge of knowledge, but something woven into its center. Polaris shines above us, not only as direction, but as a reminder that to measure is not to master, that the act of seeking truth is itself the compass, and that the journey matters more than the arrival. For cosmology, the star's refusal to yield is a warning that our most careful constructions, the distance ladder, the Hubble constant, the expansion of the universe, rest on foundations that can tremble. But for philosophy, it is a revelation that trembling foundations are part of existence itself. The cosmos is not a cathedral of certainty, but a wilderness of questions. Polaris is the guide, not because it gives clear answers, but because it keeps us searching. The North Star has always been about direction. Once it pointed explorers across oceans. Now it points us toward humility. It tells us that the pursuit of knowledge is not about closure, but about continuity, about the willingness to live within mysteries that refuse to end. Its light crosses centuries unchanged, but its meaning shifts with us, reminding us that the stars are not just out there. They are within us, shaping the way we think, feel, and dream. Polaris burns not as a solved equation, but as a poem written in contradictions. And perhaps that is its gift. A universe without riddles would be a machine, predictable and sterile. A universe with stars like Polaris is a story, vast, elusive, endlessly unfolding. The story of the North Star is not about a Cepheid that will not be measured. It is about humanity, standing beneath the sky, daring to measure, daring to seek, daring to be humbled. And in that daring, finding a deeper kind of truth, not certainty, but wonder. The mystery of Polaris lingers not in its equations, but in its symbolism. To the naked eye, the North Star is exactly what myth has always said it is: constant, unshifting, the one fixed jewel in a wheeling sky. To the telescope, it is something else entirely: restless, irregular, full of contradictions. In that tension lies the essence of its meaning. For centuries, we believed that science would teal away myth and leave only truth. But Polaris shows us that truth itself can be layered, like light refracted through glass. At one distance, the star is constancy. At another, it is change. Neither view is false. Both are incomplete. Perhaps this is what the cosmos has been telling us all along. Reality is not singular, but relative to the eyes that see it. In a way, Polaris is a teacher, It forces us to confront the fragility of our certainties. We imagine we know the universe because we can map galaxies, weigh planets, and trace the echoes of the Big Bang. And yet, here is the North Star, the very star that defines direction, reminding us that we cannot even measure our own compass without contradiction. It humbles us, reminding us that even when we stand beneath the heavens, with instruments more powerful than any in history, the universe still has the power to withhold clarity. But humility is not defeat. In fact, it may be the deepest form of wonder. When we accept that mystery endures, we begin to see knowledge not as conquest, but as relationship, a dialogue with a cosmos that answers in riddles. Polaris does not need to tell us its distance with precision to give us meaning. Its meaning lies in its refusal. It is the reminder that truth is not a single point, but a horizon, always receding, always pulling us onward. For cosmologists, this means that the universe is not finished with us. The tension in the Hubble constant, the uncertainties in stellar evolution, the flickering doubts in our measurements, all of these are invitations. They are signs that more physics waits to be discovered, that the cosmos is deeper and stranger than our textbooks describe. Polaris, by breaking the rules, may be pointing us toward the next great revolution in understanding. For philosophers, it means something even larger. It means that certainty itself may be an illusion, that the stability we crave is always provisional, always dependent on perspective. The North Star has guided explorers home across oceans, but perhaps its truest guidance is toward humility, toward acceptance that permanence is a dream we project onto a restless universe. And for the human heart, Polaris carries still another message. It reminds us that beauty does not lie in perfection, but in imperfection, not in clarity, but in mystery. A flawless star, obedient to every law, would inspire less awe than this imperfect one, which burns steadily above while hiding turbulence within. Its contradictions are what make it alive, and in them we see ourselves. We too are steady on the surface and restless underneath. We too carry contradictions that defy measurement. To look at Polaris is to see the cosmos and the self reflected back, each reminding the other that certainty is a fragile thing, and that mystery is not a failure, but a gift. So the story closes not with a solution, but with a vision. The North Star remains unresolved, its distance contested, its heartbeat irregular, its companions disruptive. But its light still falls upon Earth, as it has for millennia, a compass in the night, a beacon of wonder. And perhaps that is the truest resolution. That some mysteries are not meant to be solved, but lived with, guiding us not to answers, but to deeper questions. In the end, Polaris does not defy us. It completes us. It reminds us why we look up, why we measure, and why we wonder. Because in its refusal to be fully known, it keeps us searching. And searching is what makes us human.